was deriving the Boltzmann distribution that maximizes the multiplicity of its associated macro state. Okay, and so in the non-Boltzmann limit, low temperatures, this is the distribution that dominates, and then in the limit of high temperature, when the occupation number is low, you have this result here with these different forms of the partition function. Okay, like if you're summing over the energy groups with Cj states in each group, then you have this form. You could also sum over the individual energy states, just sum over I, and then we also talked briefly at the end about summing over the energy levels, and then the GL is the degeneracy, meaning the number of states that have the exact same energy. Okay, and you sum over the energy levels. Okay, and the point of all this was that we could relate the statistics back to the thermodynamics. Okay, we wanted to get at the entropy because we know that there's this Boltzmann relation that is the following. Okay, and then omega. We can write this basically approximately as KB as the natural log of the multiplicity of nj star. Right. Okay, so that's this. We're going to be able to plug in this optimal nj into our expression for w of nj star, and get an expression for the entropy in terms of like the energy levels. And then we'll be able to solve for what beta is in short order, basically, once we go back to earlier in I think it's chapter 3. And chapter 3, where we talk about all the different like thermodynamic state variables and all the different relations, and we'll be able to see what beta is pretty simply. And then we'll also be able to write those thermodynamic state variables in terms of partition functions. So that's what we're doing today. But first, I figured we could go over some justification for this form for the entropy. Okay, it's like not necessarily a derivation, but it would give it some justification, perhaps why, like Boltzmann chose this function. So the first observation that we'll make is that entropy is an extensive property. So if you have two states with entropys S1 and S2, their total entropy should be the sum of S1 and S2. Okay, that's not too complicated. So we'll actually just start here before we start talking about it. Let's just say that entropy is some function of the multiplicity. We're trying to find what that function is, just for the sake of discussion. Going forward, let's think about this right now, okay? And so we know that entropy is an extensive property. So then we can write this as something like the entropy is a function of, it's like the total multiplicity omega is equal to the sum of the multiplicity of system 1 plus the phi of the multiplicity of system 2. Okay, so this is like our first hint as to what form phi has to take. The other thing that we know is that the multiplicity of the composite system is equal to the product of the multiplicities of the two subsystems. Okay, just from like enumeration, from statistics. Okay, and so what this tells us is that we can modify this, and now it's like this is omega 1 and omega 2. Phi of omega 1 and omega 2 is equal to phi of omega 1 plus phi of omega 2. And then what we'll do is we'll differentiate this expression with respect to omega 1 first, and then we'll differentiate it with respect to omega 2. Okay? So if we differentiate it with respect to omega 1 first, let's do like this. Let's say we're going like this, e omega 1. That gives us an omega 2 out front for the chain rule. And then we have phi prime of to differentiate with respect to omega 1, so then we just get phi prime over omega 1 on this side, and then the other term drops out. And then we'll do another derivative with respect to omega 2. Okay, and then this term on the right is going to go away, but we have a product rule thing going on here. So we have phi prime of omega 1, omega 2, plus the phi 2 times phi 1, phi 2, yeah, right, because well, you have to do the chain rule here. So phi 1 times phi 2 times phi double prime of omega 1, omega 2. I think I keep on saying phi instead of omega, but that's okay. Okay, and then this thing is equal to 0. Not equal to 0, sorry. This is equal to, no, this is okay, yeah, it is equal to 0 because we differentiated the other side, and the other side was not a function of omega 2. Okay, and then omega 1, omega 2 is just omega. Okay, so we'll continue over here, and we end up with is a differential equation that is of the following form: big omega phi prime omega plus phi prime of omega is equal to 0. Okay, and the general solution to this, is phi omega is equal to a times the natural log of omega plus b. Okay, and then b is just like is just a constant. You just call it b we just do this like s naught. In most formulations, we just choose to set this to 0. It's like a datum. And then a, you would have guessed, is a Boltzmann constant. Okay, so there's sort of a justification for this relation, just from these two observations. That it's extensive, and then the multiplicities of the multiplicity of the total system is just the product of the multiplicities of the two constituent systems. Okay, so now we will go ahead and substitute in our optimal distribution that we found here into this formula to try to write the entropy in terms of the partition function. Okay? So we have that the natural log of omega is approximately equal to the natural log of nj star. Okay, whoops, w of nj star. Okay, and just to remind you guys what w of j star, you can look back at your notes, but what it is, it's the sum over j plus or minus cj, natural log of 1 plus or minus nj over cj plus nj, natural log of cj over nj plus or minus 1, with the plus being for both sign statistics and the minus being for interaction in this case. Okay, this is before the sign flip occurred. Okay, and then what we'll do is we'll take this thing, this nj over cj, and we'll sub it in to where we say nj over cj. We actually won't sub in for this nj right away, because in the end we'll be summing over all j, and we'll be able to just plug in like a capital N there, some overall energy into the nj's. You're going to end up with the total number of particles, right? So let's go ahead and make that substitution, okay? So have the summation here, plus or minus cj here, natural log of 1 plus or minus that one over there, okay? 1 over x alpha plus beta epsilon j plus or minus 1 minus plus. Okay, we're going to work in the Boltzmann limit anyway, so it won't end up being important. Okay, and that's instead of that one, this one, we have nj, natural log of cj over nj, so now it's inverted, x of alpha plus beta epsilon j minus plus 1 over 1 plus or minus 1. Okay? And then there's a couple of things. The first thing, like I said, we're going to work in the Boltzmann limit. So like we said in the Boltzmann limit, this exponential term becomes very large. So all these plus or minus 1s become irrelevant. Okay? And the other thing that we're going to observe, so like this thing becomes like natural log of 1 plus or minus x of minus alpha minus beta epsilon j. Okay? And that term is, so anytime you have the natural log of 1 plus or minus something very small, you should be thinking of Maclaurin series, which is just Taylor series about x equals 0. You should be thinking of this thing. Okay. That the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3, and so on. Okay. This is the Maclaurin series for natural log of 1 over x. Like anytime you see 1 plus something small, you should think, oh, okay, I can use this approximation, and this is very, very small, right? So we can just truncate at the first term. Okay, we'll just like draw in here, and so we can see this natural log of 1 plus or minus exponential of this is just going to end up being the exponential of that. Okay, so there's that, and then we also obviously have the other half of the expression, which is just nj of natural log of, once we got rid of this, we were then comparing this to plus 1 again, so then that goes away, and it's just the natural log of x plus beta epsilon I. And yes, the natural log of an exponential is the argument, but we'll leave it in that form for the time being. Okay? So we have this, and then once again, this goes away as well, because, oh no, sorry, not in this case, not in this case. This is the Maclaurin series argument. So, let me just write that down really quick. So, oh yeah, and then the plus or minus here is going to cancel with that plus or minus, because you either have plus plus, which is positive, or you have minus minus, which is negative. So you're going to take this whole thing as x, and that argument over there, and so this entire thing becomes equal to just this part, and then plus plus is positive, minus minus is positive, so you just end up with Cj times the exponential minus alpha minus beta epsilon j. Okay? And then plus nj natural log of x alpha plus beta epsilon j. Okay? And then also, this is where we'll bring the partition function into the mix, because we know that e to the minus alpha is equal to n over q. Okay? And then q has all this form. We'll use this form at first, but we'll actually be writing everything in terms of q, so it's not super important. And so what this ends up being is the following. Still summing over j. You have Cj n over q. This is just the x with minus alpha times x beta epsilon j. Okay, that's the first term. And then the second term is plus nj, natural log of q over n. This is where I'm going to split that natural log into two pieces. So the first piece is natural log of q over n, that's this piece, plus nj beta epsilon j. Okay? And then, let's pull this one. So now we see why we left the nj around, because we can, this is the only term in this term that depends on j, And then these are the only two terms in this term that depend on J. So if you sum up Nj epsilon J over J, you're going to get the total energy E. If you sum up Nj over all of J, you're going to get the total number of particles, of course. And then the other thing is, the sum over J is Cj x the minus beta epsilon J. That is exactly the partition function, right? So the Q's are going to cancel in this expression. So the final expression that you get for the entropy looks like this. So you have, and we put a KP up front because I think we were just looking at the natural logarithm multiplicity here. So we're going to apply a K to the whole expression, and you'll have Kn. Okay, that's the first part. Like I said, the partition function will cancel. Plus N. Sum over all J of Nj is equal to N. The log of Q over N. Okay. And then we have just the total energy times beta E. Okay. So this is just a function of Q, and the total number of particles, total energy, and beta. Okay. So this is nice. Now, typically, the total number of particles is something that you would know, and that total energy as well. These are we're getting close to like state variables now. Total energy is state variable, and then the partition function we'll see later in this lecture we can construct by knowing facts about our system, how it's structured. Okay. Yep.
Should the K be distributed among?
You're correct. Yes. All right. Let me see real quick. Yes, you're right. Just make sure yeah, they should be distributed. Makes sense. So this is the proper function. Okay, and so now observing that this is the case. Okay, we're going to write down a total differential of S. Okay, and we're going to see if we can look back. This is where we're going to start having what I would call like a dance of thermodynamic state variables. Okay, so in thermodynamics, what you do often is you define these state variables, and we're going to see several. Today we're going to see like a Helmholtz free energy, a Gibbs free energy, and what you do is you take total differentials of them, and then you look at the partial differentials next to like the different d's, like ds, dt, dy, and you equate the two. So you'll see what I mean in just a moment. But first we'll start with taking the total differential of the entropy, assuming that it's a function of these variables, right? So we have ds, dn, holding q, beta, and e constant, dn, ds, de, holding n, q, and beta constant, de. So you guys see the idea here. ds, d beta, holding n, q, and e constant, d beta, plus ds, dq, holding n, e, and beta constant, dq. Okay? And so we have these things, and then we can also just take this expression that we had before, and we can differentiate it with respect to all those things. Okay, so let's do like ds dn first. So ds dn is at holding q, beta, and d constant is equal to k natural log of qn plus k. We're gonna have to use a product rule on this one, yeah? Okay, so we have k n times n over q, product rule, chain rule actually here, over n squared plus, this is the, plus k, plus k. So you have the q's canceled here, this cancels with that one, and then the remaining n cancels here. And you have a minus. What you end up with is a minus k and a plus k, so these two cancel. So for the the derivative of s with respect to n holding all of things constant, just k natural or q over n. The derivative of the entropy with respect to the energy holding all other things constant is equal to just k beta, right? Here's here. The derivative of entropy with respect to beta holding all other things constant. See this one, just e. And then the derivative of s with respect to the partition function, holding all other things constant, is equal to kn n over q times 1 over n, which equals just kn. Okay. So we have all these different sort of functions here, and then now we're going to take a step back to thermodynamics, okay? And you may recall that we defined the Gibbs free energy in the following way. We just wrote it as, here, I'm going to draw a quick line right here. So we can, we're going to take a step back. We're stepping away from the statistical mechanics for a moment, okay? So we have the Gibbs free energy. It looks like this. It's E plus P V minus T S. Okay, and then we also the chemical potentials will come in here in just a moment, but we also define those in the following way: the chemical potentials of a certain species was just equal to dg d in S, holding like the pressure, temperature, and then the other concentrations of the species constant, like NS, right? Okay. So we have this definition, we have this definition, okay? You can also write this in terms of enthalpy, because enthalpy is just E plus PV, that's H minus TS, okay? So we have that. Now, for a reversible process, let's push this out. Pull this down. In fact, I'll write that here. So, for a reversible process, we have that dH is equal to, in general, it's equal to dE plus PdV plus V dV. Okay, so E is H is this thing. You take the total differential, you do the product of all this one. Okay. When you have when the process is reversible, so first of all, the first law tells you that dE is equal to dQ minus PdV. So then you have plus PdV here. This VdV. Okay. When the process is reversible, dQ is equal to TdS. Okay. So then these things cancel, and then dH is equal to TdS plus VdV. Okay. And so now we will take the total differential of G, the expression, just leaving H in there, and then we'll substitute what we've just written down for pH. So we look at what dG is. It's dH minus TdS minus SDT. Okay, and we just found that dH is TdS plus VdP. VdP minus TdS minus SDT. There's a method to this madness. Okay. So then we have this expression for dG. Okay. And then we also know if we're going to allow our system to be open or really if we're going to allow any of the constituents of the system to react as well, you also have to add the chemical potential component as well. So you have to have this additional part of dg, which is the following. You have to have plus the sum over s of mu at s d number of s. Okay. So this doesn't necessarily have to be here. If your system's closed, it wouldn't be there. But if your system is open, or if you have a reacting system with components where the concentrations are changing, the number of moles are changing of each species, you have to add this part here. So we're just going to put it here so we don't have to, just to relax our assumptions. We're no longer in a strictly closed system. Okay. And then now we're going to take the total differential of the first equation. Okay. So we just took the total differential of the second way of passing it in terms of the enthalpy. And we have this result from the first law for a reversible process here, and we use that. So now we're going to take the total differential of just the first equation. Okay. So if we do that, same thing, dg is now dE plus dED plus v dP minus TdS minus SDT. Okay, and then we're going to equate that to what we have here. So we have VDP, we know these are equal. VDP minus SDT plus the sum over S mu S V and S. Okay, and so we can see that these guys are going to cancel. Okay, and then we can then also solve. So now we just have one ds. So we can solve this expression, this here and here, and solve it for ds. So ds, we're going to divide by t as well. Okay, so we'll move this to this side, move the chemical potentials to the other side, and then divide by t. So you have 1 over t dE plus p over t dV minus 1 over t sum over s e at s b and s. Okay, and then if we want to, for simplicity, go back to just say that we have just one type of species, but it's still an open system, we'll just do this minus mu tilde over t d n. And just have it because we'll do on a per atom basis with tilde. Okay. So now, look, you have ds dE. So we know. So we have this. We know that ds. If we have if it's a function of energy, we have this this derivative dE. So we expressed. We know that we can equate these two things. We know we have ds here and ds here, and then the coefficient in front of dE in this case is 1 over t, and the coefficient in front of E in this case is k beta. Okay, so what this tells us is that k beta is equal to 1 over t, which tells us that beta is 1 over kt. You guys might have been expecting this result, but this is what beta is. Okay. And now it's like the Boltzmann distribution looks really familiar, right? It's like it's an energy distribution, and it's the energy value over kt. What does that remind you of? Okay, so then that showed us what beta is, and so we can rewrite our entropy function real quick in terms of just Q and energy and the temperature. We can eliminate beta from that, and we can just write entropy is nk times the quantity natural log of Q over n plus 1 all plus E over T. Okay, so this board. That all makes sense? Okay. So now we'll introduce another state variable, okay? This is a Helmholtz free energy. It looks like this. F, and it's defined as the energy minus Ts. Okay? So if we take the total differential of this, you get the following. You have dF is equal to dE minus TdS minus SdT. Okay? And then we know from before that dE minus TdS is equal to minus PdV plus mu tilde n. Okay. This is just I think that's actually just the first one. So then we can rewrite this again. The dF equal to minus SdT minus PdV plus mu tilde dn. Okay? And so what this tells us is that S is equal to minus dF dt, holding the volume and the number of particles constant. It also tells us that the pressure is equal to minus dF dV, holding the temperature and number of particles constant. And it tells us that the chemical potential is equal to dF dN, holding the temperature and the volume constant. Okay? Because those are the terms that would be here if you just if you just assume that F was a function of, volume, number of particles, temperature, and then did the total differential. Those are the partial derivatives that would appear here in this expression. So you're able to make these relationships. Okay, and then also E is equal to F plus Ts. So then this is equal to F minus T times the derivative of F over PV, holding T and N constant. Okay, and then you can rewrite this so that basically E is just a function of F, but a derivative of F and the temperature. You can write this as T minus T squared times the derivative with respect to T of F over T, holding T, or sorry, not T, and V constant. Okay? So you can recast the energy in terms of F of a derivative of F as well. Okay? Okay. So now we have the entropy, we have mu, we have the pressure, and the energy in terms of derivatives of F with respect to T, and other variables like V and N. Okay? So if we can write, if we know what F is as a function of T, V, and N, then we're good to go, right? And we can observe that the way we define this, and given our expression for the entropy, we're going to have F just in terms of N and Q and N, because you have that E over T, and then you have E minus T times S. So the E over T term will fall out. So what that means is that F itself is actually just equal to minus T N K times the natural log of Q over N plus 1. Okay? Okay, so then we can use this expression to now write our energy, our entropy, our mu, and P all in terms of just Q. Okay?
Jesse,
Yes.
where does the df/dv come from? I expected it to be dt.
df/dv. Let's see. Let me see. I think right here we're plugging in the s. So f plus ts.
That's sweet.
Oh, you're right. That should be a. Let me double check and make sure I'm not these things. Yeah, you're right. It should be df/dt. You're correct. Holding v and then constant. Sorry about that. And that's why we have dt there. Yeah, my mistake. Okay, good. Thanks for pointing that out. Okay, cool. And so now we will just carry out these derivatives of f to have all of our state variables in terms of q. And you guys are going to use these formulas on your homework and probably at least a subset of them in the exam as well. So.
So I can show you guys something.
Okay, so we have that E is equal to t squared d dt of f over t, holding v in a constant. Okay, this is equal to minus t squared d dt of minus nk natural log times quantity natural log of q over n minus 1. This is just nkt squared times the derivative of natural log of q dt holding n and v constant. And the reason that it's because you can split this natural log up into natural log of q minus natural log of n. Natural log of n does not depend on temperature, so it goes to 0 when you take the derivative. Okay, so that's why that drops out, and then the pressure is equal. And remember this. This is the formula. You're going to use this. Okay, and the pressure is equal to minus df dv holding t in a constant. Okay, and then that is just equal to dv of t and k natural log of q minus natural log of n plus 1 holding t in a constant. This is just equal to nkt times the derivative of natural log of q with respect to the volume holding the t in a constant. Okay. Okay, and then we will look at mu, which is equal to df dn holding t and u constant, dn of minus t n k times the natural log of q minus natural log of n plus 1 t and v constant. This is minus k natural log of q, yep, minus natural log of n plus t n k times 1 over n. Okay, and then there's also from this plus 1 here, you also get a minus t. So these cancel, which makes this term outside cancel. And this thing is just minus, sorry, this isn't super legible. This is just minus kt, natural log of q over n. Okay? And then, of course, q is not a function of n in all of this. So when we take this derivative, it's just a constant. So that is your expression for the chemical potential. And then we can also rewrite S now because we have an expression for E solely in terms of the partition function. Nk times a natural log of q over n plus 1 plus t times the derivative of the natural log of q with respect to t holding n and b constant. Okay, so we'll box that one too. Okay, so now we have all of these thermodynamic quantities that we're familiar with in terms of the partition function. So now, with our last few minutes here, let's talk about what the partition function looks like if we just use translational energy. So you guys recall, we talked about the particle in the box, okay? So when we're talking about translational energy, we're talking about those energy states. And you guys probably won't remember by heart what the energy levels of the particle in the box are, so I'll just give them to you. The energy level associated with the three quantum numbers nx, ny, and z is this. It's h squared over 8m times nx squared over x squared plus ny squared over ay squared plus nz squared over az squared. Okay? And so then our partition function, let's just sum over all the energy levels, okay? So our partition function, we'll call it Q translational, is the sum over nx, the sum over ny, the sum over nz, okay, of x minus nx squared over nax squared plus ny squared over ay squared plus nz squared times h squared over 8m, and then this is e over kt over times beta, which is 1 over kt, okay, which we found. Now let's just, for simplicity, say that t squared is equal to h squared, tau squared, I should say, e m kt. So we'll simplify our expression a little bit. So this is our partition function. We know what it looks like in this case, where we're only considering translation energy. And so what we can do, because the exponential is a product that we can split up, we can then take the components of this multi-layer sum and split them up in the following way. You can just do nx of x of minus nx squared tau squared over x squared. Okay, and then you just have ny, and then it's like the same thing except for ny, ay squared. Okay, and then you have the sum over nz, and then it's the same thing. Okay, so you split it up into three components. All the components look like this, and then we note that tau squared over a squared is very small. Tau squared over a squared for the hydrogen atom in regimes that we're interested in, ax squared, is on the order of 10 to the minus 16. Okay? So what that allows us to do is it allows us to recast this sum, this discrete sum, in terms of an integral with almost no error. Okay? And then we know what this integral is. So we're going to take the sum over nx of the exponential minus nx squared tau squared over ax squared. And we're going to say because tau over ax is very small, I'm not going to explain. I'll explain if you guys want to stay after class, I'll explain why this assumption makes sense. But I want to get to the final result here. So this is the same as integrating over the right side of x minus nx squared tau squared over ax squared dnx, and we recognize this integral. Okay, it's just like a Gaussian integral, and you get ax times square root of pi over 2, because you're only integrating over half the support, tau. Okay, so this is just like your pi over a. Since we have a tau squared over a squared here, when we take the square root of there's whole values there. Okay, so then we can rewrite our translational energy partition function like this. So we can see that the partition, the Q translational is just a product of three of these integrals. They're all identical. So except for they have an AX, AY, and AZ. So Q translational looks like this. It's equal to AX, AY, AZ over 8 tau to the third times pi to 3/2. Okay, and then we can substitute. So there's a couple things. AX times AY AZ, that's just our volume. Okay, so that's just B, and then we have an 8 on the bottom, and then we can substitute back in our definition for tau, which is like tau is the square root of this quantity here. So then we can write this as 8 MK T pi over h squared to the 3/2. Okay, and then we'll bring that 8 in there. And then our final expression for Q translational is V 2 pi M KT over, sorry, it's in the shade a little bit, h squared to the 3/2. Okay, this is an important formula. We'll frame it. Okay, you can see it. Okay, so that's our partition function associated with translational energy. Okay, so now we can look at, and I covered some of them, but we can look at the expressions that we have for the energy, the pressure, and the chemical potential. We can evaluate it using our formula translational, and we're going to see some very familiar results. Okay, so P is equal to NKT times D natural log of Q over dV holding T and N constant. Okay, so if you take the natural log of this value, you can see that you can just split it up because it's a product. Okay, so all this other stuff does not depend on V at all. So this is just what this is going to amount to is you're just going to have NKT times dV of natural log of V. Okay, that's just 1 over V. So this is an NKT over V. So you get PV equals NKT. It's just ideal gas law. So like this, I think this is so cool. So like, look at this. This is from quantum mechanics. Okay. And we constructed the partition function. And remember, we arrived at these formulas first by doing this crazy optimization where we were enumerating states. But we just counted up states, okay? And that allowed us to get these formulas for our thermodynamic quantities of interest in terms of the partition function. And then we constructed our partition function with the quantum mechanical energy levels, and we recovered the ideal gas law. Like I think that's so great. I think that's so exciting. I don't know about you guys. So like, let's do the energy real quick too. I know I'm a little over time. Let's just at least do the energy, okay? So the energy is NKT squared times the natural log, the derivative of the natural log of Q with respect to temperature this time, holding N and V constant. Okay. Again, we'll just take. So we're taking the derivative with respect to the temperature. So we'll just take the part that depends on the temperature out of the partition function. The derivative of the rest is just going to be 0 because you can split it up into a sum. Okay, so then this becomes NKT squared times the derivative with respect to temperature of 3/2, bring the exponent down, of the natural log of T. So what's this? This is 1 over T. So that's going to cancel with this thing, and you're going to end up with 3/2 kT. And NKT, sorry. Which is like, this is the equidistribution of energy theorem. We've seen this before. You know, I think this is like, this is really great. So, I'm out of time, so I won't do the entropy. I'll leave you to do it on your own. But in the end, the punchline is that you get the relation. You can recover the relation for a specific energy or specific entropy of a thermally perfect gas that we've seen before. That basically just looks like this. It's like times the natural log of P times R. This is a lowercase s. We're now on a mass basis. Okay. Times the natural log of P plus like some sort of like constant. Okay. And then this also allows you to say that Cp is equal to 5/2 R. Okay. So this is you can find this on your own. It's not too hard. Just using this formula here. But these two things I wanted to get to before we were done because I just think it's astounding that we took this long winding road, but we started with such fundamental concepts. Okay, we were just counting states, and then we arrived at the ideal gas law. This thing that we've been using for weeks and weeks and weeks. So I think that's probably a good place to stop. We're a little over time. But does anybody have any questions? Thanks, guys.